Hello students, welcome back. We just completed 4.1 and 4.1 is all about the order formula of finite cyclic group. It is the smallest positive integer such that the generator to that power is E, the identity. And then we can rewrite the same set in a little bit alternative fashion. Instead of a to the nth power and a to the 0 power only, I can generalize a little bit further. And then instead of n minus 0 only, it could be something more arbitrary. So if k is equal to 0, then it's the same as that. The equivalence can be proved like this, and n is h minus k basically, and we can make it positive because without loss of generality, we can assume h is greater than or equal, and if they're equal to each other, then we just have trivial set E, so no problem there. That's not what we want. In any case, we already proved that these two are equivalent. Sometimes we use this for simplicity, sometimes we use this for convenience. And then we went through the proof, and the main tool we used was the division algorithm. Yes, we can use the division algorithm because m belongs to a set of strictly positive integers, so you can divide by m. And then, as an immediate consequence, we have this divisibility property. The generator to a certain power is the identity E. Then, that power is divisible by the order. I didn't prove it. It's a homework problem, so everybody has to do it. One direction is, as a matter of fact, pretty straightforward. If m divides n, that means n is some integer times m. In general, you have qm plus r, but r is 0 because m divides n. Therefore, a to the nth power is a to the qm power, and that's a to the m power to the q power. And what is this a to the m power? It's E because m belongs to this set. So it has to satisfy this purple condition as well. So e to the q power, and that's E. And that completes the proof of one direction. It's the other direction that you have to work on. Good luck. That's a homework problem. Now let's go to 4.2, and this time let's establish a similar divisibility property, this time for subgroups. Let's begin with a finite cyclic group generated by A, and then let's select any subgroup. Remember, every subgroup of a cyclic group is cyclic, so it has to have a generator, and the generator of course has to be a to the certain power form because everything began from a cyclic group generated by A, so everything is a to the certain power form. Let's say this subgroup is generated by a to the s power, and let Q be the order. Then we have these two conclusions. M divides s times q. The order of the original cyclic group divides the product s times q, the power of the generator of the subgroup times q, the order of the subgroup. So m divides s times q. And then second conclusion, q divides m, the order of the subgroup divides the order of the original group. And this is for non-trivial subgroups, but as a matter of fact, I'm pretty sure this works for trivial subgroups too. It's just that our textbook author did not consider the case. In any case, let's prove it. We have two conclusions, so we need two proofs. Proof for the first conclusion, m divides SQ. Okay, let's go ahead and do that. First, make this observation. A to the S power has order Q, you see. This generator, A to the S power, generates this subgroup, and that has order Q. Therefore, A to the S cube power can be rewritten A to the S power to the Q power, and that's E. Remember, that's the generator. And then we have Q power. Just look at the screen. Yeah, I should have highlighted this entire thing as green. Look at the screen. A to the S power is a generator, and it has order Q. So generator to the order, you have to have E. Now from here, let's apply this. A, which is the generator of the original, has order M. So this SQ power has to be divisible by M. See that? From here, in place of N, I have SQ. And I don't need double arrow as a matter of fact, even though it is true. So that's the conclusion you get. Let's review. The subgroup has order Q. So this generator, A to the S power, has order Q. And we're going to use that. A to the SQ power can be written as A to the S power to the Q power using the exponent rule. But then again, look at the screen. A to the S power is the generator of this subgroup that has order Q. So that's the Q power, that's E. So generator to the order power is E. Also, look at this. And then we use this. Generator to a certain power, SQ power is E. So the order M must divide that power SQ. Okay, we are done with the first. Now let's prove the second. And that's going to be a little bit trickier, not because difficulty, but some of the characters here are confusing. Okay, let's begin. First, observe that A has order M. So A to the M power is going to be E, yes. So let's make this observation. A to the S power to the M power. You can rewrite it as A to the M power to the S power. A to the M power is E, so yes, we have E. A has order M, so yes, M power is E. But then again, let's go back to the screen. This subgroup is generated by A to the S power, and that has order Q. So this generator, which I just highlighted in blue, highlighted in green, excuse me, to the M power is E. So this power here must be divisible by its order, and that order is Q. Can you read it better? Maybe a little bit bigger fonts may help. A to the S power to the M power, we can rewrite like this, A to the M power to the S power, and that's E. Oops. So this thing to the M power is E, but that thing is actually the generator. So generator to a certain power is E. So that power is divisible by the order, and order is Q. Look at this. M and N are, I'm using same M here and there, so that's causing a bit of a confusion. But if you reread this thing into generator to a certain power is identity, then order divides the generator. If you read it like this, then it makes a lot more sense. Because A to the A is power, this one is generator of this subgroup. Not the entire group, but its subgroup. So generator to this power is E, then that power is divisible by the order. The order of the subgroup is Q. And M is the order of the entire group, but it happens to power this time. Consequence, Q divides M. We get the second conclusion as well. So we proved both. M divides S times Q, the product of the power of the generator of the subgroup times the order of the subgroup. And second, the order of the subgroup divides the order of the original group. It'll turn out, however, this one here, which I just highlighted in bold, is going to be true for all finite groups, not just for cyclic groups, but for all finite groups. So any finite group of order M has a subgroup of order Q. They don't have to be cyclic. Q must divide M, and that's something we're going to prove in a couple of weeks. Here we did only the subgroup version, cyclic group version of that. Let's see, do we have enough time for a little bit of addendum here? Let's talk about it. I de-emphasize this non-trivial part in gray because I think it is true without this restriction. Let's see, what do you mean by non-trivial? A to the S power should not be E, but if it is trivial, A to the S power is E, that means S is 0, right? In that case, S is 0, then we're going to get a trivial group. When S is 0, is this true? S is 0, then this one is 0. So M divides 0? Yes, that's always true. 0 is always divisible by everything. Also, if this is E, then it has trivial group. It has only one element E, so Q is 1. And Q divides M, that's always true. 1 divides everything. So both conclusions are true, even when this is a trivial group. So I think this non-trivial condition is unnecessary, but I didn't want to deviate too much away from our textbook, so I just kept it. But actually, you can extend it a little bit further. It doesn't have to be non-trivial. It's always true. Okay, so much for 4.1 and 4.2. Let's discuss the other in a separate video. See you soon.